Okay, there's a maximum deflection. You've got a total deflection here. That means the end of the proof mass. So not only the tip of the beam. Okay. Now we consider resonant frequency. Resonant frequency tells us about how fast the system can follow up our signal. So when we have a sound signal input into the system, if the signal is too fast, vibrate too fast, in order that the system cannot follow, so there won't be any signal coming out. So it's important to design our system has a fast enough frequency response to follow up your signal. So the resonant frequency will be equal to the omega n equal to k over n. K means the spring constant, n means the mass. Okay, so you have a large K, small n. You've got a very large omega n. That means you have a wide frequency response, so you can follow up faster signal. However, if you have a small k, large m, that means you have a small omega n. That means the speed of the system will become slow, very slow. So you cannot follow up a very fast, rapid signal coming in. Okay, so we consider all the parameters, not only sensitivity but also the speed. So when you consider you want to have a very high sensitive sensing, usually we were using softer spring. Actually, softer spring can give a larger displacement and a more deflection and a more strength. However, in that case, the frequency response will be sacrificed. The system will become slow. So it's not easy to design the system fast and also very sensitive at the same time. When you consider these two together, yeah, it's some contradiction. So that's why you need to wisely select the parameter in order to not to sacrifice one parameter too much, in order to trade off to get enough signal from the system. So that's the beauty of the design. Okay. Now we come out to the final parameter we call the responsivity. Responsivity, that means the response between the output signal and the input physical quantity. In our case, will be the output voltage. That's the final result we want to have. And over the input physical quantity, we call it acceleration. Okay. So the ratio between the output voltage and the acceleration will be the responsivity of the system. Okay. So in order to get the output signal as a voltage, so we need to put our resistor into a Wheaton bridge, for example, like this. So in the Wheaton bridge, we have the 4 resistors. The 4 resistors, they can have the same similar resistance, or they can have some kind of spatial ratio. Here I demonstrate only of them with the similar resistance. For example, the original resistance, all are R. Okay, they are equal. Okay, so when you apply voltage on the top and give the ground at the bottom, so you got a 2 voltage here, V plus and V minus. If 4 resistance are the same, you got a V plus equal to V minus, right? No problem. So in this case, V plus minus V minus will be 0. There will be no voltage difference. However, when we have some kind of deflection, the resistance change, for example, increased. So, for example, if the resistance is increased in this condition, so V minus will become lower, V plus will become higher, right? So the delta V will become some kind of value, okay? So if you change more on the resistance, the difference between the voltage here will become even larger. So the voltage difference here will be proportional to the delta R, okay, according to the situation I just mentioned, okay. So these things can be calculated accurately by solving the circuit using the equations on the bottom. So V plus will be it's kind of voltage divider. So the voltage will be divided by the resistance on the bottom here. Okay, so the total resistance will be R 2R plus delta R. And the voltage divided here will be R over 2R over delta R, okay? So the other one is divided by this one, okay? Okay, so the difference will be the voltage variation here. So end up you'll find out the voltage difference will be proportional to the resistance change. This is a linear relationship here, okay? And you want to have a higher voltage change, you need to have a higher resistance change. That means you need to put your sensor in a more sensitive region to the strength variation. You have a larger strength variation, you get large resistance change. You also got a higher voltage change, okay? And on the other hand, you can also consider using smaller resistance, okay, or higher resistance. They also will change your delta V. But you remember, if you increase the resistance, actually the resistance change will be increased. So there won't be much, differences when you are doing this. Okay, they will vary, change at the same time. So another thing you can consider to increase the voltage changes by giving a higher driving voltage, VE. If the driving voltage changes 10 times, you got a more voltage output here. But sometimes you also need to consider the ability for the resistance to sustain different kind of voltage. If you give too high the voltage, the resistance can be burned out easily. So there's still some physical limitation. You cannot give any kind of voltage you like. So typical voltage will be from 10 volt to 100 volt. If you give 1,000 volts, usually it's not typical. Usually will damage the circuit. Okay, 10 to 100. So there's some limitation. Okay, so finally we will get the final equation. So when you have this kind of equation here, and the delta R has been derived previously, so you can plug in the delta R here, and you get the final equation here. The resistivity will be like this. So this value, this final equation is important. You can consider to separate it into 3 different groups. The first group will be the input voltage. The second group will be the material property. The material property will be like your gauge factor, Young's modulus, and the resistivity. These 3 will be the material property. And the third one, the last one, will be the geometry parameter. Okay? So the rest of like Z, like T, W, L, P, A, and B, those things can be grouped into the number 3 group. The number 3 group corresponding to the geometry of the structure. So in your design, actually, when you have selected the fabrication technology, for example, like CMOS, it's not easy to change your gauge factor anymore because you already selected the material. For example, like a polysilicon, so the gauge factor will be fixed. When you select a polysilicon, the Young's modulus is also fixed, and the resistivity depends on the doping level. Because if you select the TSMC's fabrication process, the resistivity is also fixed. So when you are using CMOS process to do your design, actually the material property are fixed. You just select them, okay? So you cannot do too much design on that parameter, remember. And the voltage you can manipulate a little bit from 10 to 100 volts, depends on your needs, okay? That's a limitation. And the only things you can do the design is by changing the parameter like the geometry parameters. That's the only things you can do. And from the geometry parameters, there are 2 different groups as well. The first group regarding the thickness of the material. The thickness of the material, like the thickness of the beam, A. Z is the position between your sensor to the neutral surface. And also the thickness of the proof mass. Those things regarding thickness is also not very easy to change. Because when you select the CMOS process, the polysilicon, the cantilever beam, the silicon dioxide structure, the thicknesses are fixed, right? So you can maybe do several combinations. For example, like your beam. Currently, we are using 4 silicon dioxide layers to combine together to give you the thickness of the beam. If you want to make this thinner, in order to make it more sensitive, so it's also possible to select only fewer layers, not only another 4 layers, maybe 1 or 2 layers. But at the same time, you also change the Z, the position of your sensor, to the central neutral surface as well. Okay, so the complexity is for real design. You need to consider all the parameter variation. They will affect each other. So the final result will change. So you need to choose them wisely. Okay, for example, the thickness you cannot change. So the only parameter you can do a lot of the design is the top view geometry. From the top view, you have the geometry like the width, the length. Those 2 parameters are the most parameters for you to design at the first time. When you are looking into some kind of a structure, the first things you can look into and do a lot of design is the width and the length. Consider that. Then the second one, you need to consider like the thickness. But if you choose a certain kind of a fabrication process, the thickness may not be changeable that much. And the third parameter you will consider will be the material properties. But remember, if you already select the fabrication process, the material property cannot be changed too much as well. Okay, so I encourage you to follow my instruction and try to group this kind of equation into 3 important groups, including the input parameter like the voltage. The second one will be the material property, like the G, the gauge factor, the Young's modulus, and also the resistivity, though you put these 2 together. And in the third group, you will have 2 different kinds of subgroup. One is the thickness, the other one is the width and the length. Okay? Understand? Because that will appear in your midterm, second midterm. I won't do that for you. You need to do it by yourself, okay? So R equal to 1 group, 2 groups, 3 group. That's the input parameter. For example, like the second one with material property. The third one was geometry. For the geometry, there are 2 subgroups. The thickness width and the length. Yeah, so it's important. Okay. So it's important for you to come back home, take this as a homework, and try to split those parameters into these 3 groups, and also the geometry into 2 subgroups. So when you are doing the design, you need to start with the easiest part to start your parameter change first. That means the width and the length. You can start the design from the width and length. Then consider the thickness. Then consider the material property. Okay, those things. So that will be easier for your design. Otherwise, there are too many parameters. It's not easy for you to consider them at the same time at all. Not easy. Okay? Okay. Now we come back to the responsivity. So you want to increase the responsivity from the design parameter. Several things you can do is first the width of the plate and also the length of the plate. You can increase them. And the most effective one is the length of the plate. You can see it's a square rule over here. So increase the length of the plate, the proof mass. You can increase this a lot. Then you can consider the width of the plate and also the thickness of the plate. Thickness of the plate is not that easy. And another one is by controlling the position of your sensor, the value of a z. So the sensor need to be put as far away from the neutral surface as possible. Okay, the best position will be the ulterior surface. Okay, of the beam here. So you still have some silicon dioxide layers on the bottom. There's a field oxide. You cannot get rid of them. Okay, so if you want to make this distance further, you need to consider using different layers combination. But not they're easy, yeah, because you already have some intrinsic restriction over here. So that's a z parameter. And another thing you can consider is the B is the width of the beam. So you reduce the width of the beam, you can increase the responsivity as well. But there's still some limitation because you need to have some certain kind of thickness in order to accommodate your sensor on the top of the beam. We cannot use in very, very thin beam. Okay, so still some limitation. So according to this equation, actually most of the things you can use is LP and also the W, the length of the proof mass and the width of the proof mass. These are the two most important parameters for you to design. Okay, others are not easy to do. Yeah, and also the length of the beam. Okay, yeah, and if we try to increase the proof mass, increase the LP or LW, actually you are reducing the frequency response because remember the frequency response. Yeah, that means LP, LW is over here. So if you increase W and LP, you decrease the frequency response. But the effect is different. In the responsivity is a linear relationship to the width and the LP. For example, LP here is a square, right? R equal to a square. So you increase the LP twice. You increase this 4 times. But at the same time, you decrease the omega n by 2 square. The effect is different. So you gain 4 times of a responsivity, but you reduce only square root 2 of your frequency response. So sometimes it's a trade-off. You trade a little bit your frequency response, but you gain a lot more responsivity. Okay? Depends on your needs. Sometimes maybe you sacrifice a little bit of frequency response, but you gain a little more responsivity. Maybe it's a good trade for you. Okay? Think of that. Yeah, so in the design, you need to consider parameter, not only single, but several together. Okay. Now, noise. Okay, Johnson noise. Noise will take a lot of time to explain, so maybe we leave those things in the next week.